Okay, so our next speaker is Nicolas Guigui from the Université Côte d'Azur. And so he will speak again about priority transport, a reduced priority transport equation for Lie groups with a left invariant matrix.
Thank you. So hi, everyone. My name is Nicolas. I'm a third-year PhD student working with Xavier Pennec in his ERC on geometric statistics at INRIA and Université Côte d'Azur. And I will speak today about a formulation of parallel transport for Lie groups with a left invariant metric. So Lie groups, as you may know, are ubiquitous in many applications, in navigation, robotics, computer vision, or medical imaging, for example. And a plethora of structure-preserving methods have been developed to deal with data that lie on manifold, ranging from numerical integration schemes or optimization schemes, or more recently to machine learning on Lie groups. And these methods allow to leverage the structure of the group to act as a prior and be able to be more efficient in the computations, more stable, and use less data. And one of these structures that we can use are invariant Riemannian metrics, which allow to measure distances between elements of a Lie group and also define geodesics and parallel transports. And as we've mentioned already with Elodie in her talk, parallel transport is a fundamental tool in statistics. It allows to generalize many procedures, and it's been used, for example, in transfer learning or in batch normalization. And in both cases, it was to map data from one point to another in order to reuse a model that was learned with data at one point. Or in shape analysis, it can be used on longitudinal data to normalize the deformations that are represented by elements of a group. However, computing parallel transport is not straightforward, and some methods have been developed. For example, the fanning scheme that works on the it's been used mainly on the group of diffeomorphism for shape analysis, and it's based on Jacobi fields. It's a first-order approximation of parallel transport, or ladder methods, which you've seen already with the pole ladder, that use only geodesic parallelograms, and so the exponential and logarithm maps. And in this work, we've derived a reduced parallel transport equation in the sense that it will be expressed only in the Lie algebra, similarly to the geodesic equation. And it results in a generic open source implementation that is quite stable numerically, and that we will exemplify on the Euclidean group in dimension 2 and 3. And we compare this implementation with that of the pole ladder on this group. So to begin, we consider a Lie group G and its Lie algebra fracture G, which is identified with the tangent space of the group at the identity, and also with the set of left invariant vector fields. And we define on G a left invariant metric, which is thus defined by an inner product in the Lie algebra. And that verifies on the whole group this invariance property, meaning that the left translation, LG, is an isometry. And further, we define the dual adjoint map with respect to the invariant metric, as the usual adjoint in the Lie algebra. And to compute the parallel transport, we are interested in computing the Levi-Civita connection of this left invariant metric. And the connection is also left invariant. So it is determined by a bilinear form in the Lie algebra, which we can compute explicitly, and it derives directly from Kosul formula and by the left invariance. And as you can see, it only depends on the bracket and on the adjoint of the bracket. So with a basis of the Lie algebra, it can be computed very easily. However, this expression is only valid for left invariant vector fields. And in order to compute the parallel transport, we generalize this formula to a vector field y that is defined along a curve gamma. And to do so, we need a basis of the Lie algebra that is extended to a left invariant basis of vector fields, well, a basis of the left invariant vector fields, but it's also a basis of the module of vector fields, meaning that we can decompose y and gamma dot, the velocity of the curve, in this basis, but with functional coefficients. And we define the corresponding left angular velocities that are the pullback of y and gamma dot. There's a type, no, that's no typo. So the pullback of y and gamma dot, so there are quantities expressed in the Lie algebra that depend on time. And now we can compute nabla gamma dot y and its pullback by the left translation. And we obtain this formula in which we retrieve the bilinear form alpha, and a correction term zeta dot, that is the evolution of the left angular velocity in the Lie algebra. And now we're interested in two particular cases of this equation. In both cases, we set the left-hand side to 0. So the first case would be of a geodesic curve gamma, and it's very well known. It results in the Euler-Poincaré equation that is expressed only with the dual adjoint because alpha reduces to the dual adjoint when x and y are equal. And in the same spirit, we are interested in the case where y is parallel along gamma. And again, setting the left-hand side to 0, we get this formula. We obtain this formulation of the parallel transport of the vector y along gamma if it verifies these equations, in which the first two mean that gamma dot and zeta are the left angular velocities, and the third one drives the evolution of zeta. And similarly to the Euler-Poincaré equation, we can integrate this equation with a numerical scheme in order to approximate the parallel transport on a Lie group. And so now I will exemplify this on the group of rigid body transformations, SE3, equipped with a left invariant metric G that we define at the identity, so in the Lie algebra, with the canonical inner product, but we add an anisotropy in one direction of the translation with a coefficient beta. So when it is equal to 1, we retrieve the canonical left invariant connection that results in a direct product of the rotation group and the translations, whose geodesics are the one on the upper left plot. And so there are straight line and constant velocity rotations. And this space is locally symmetric. But if beta is different from 1, then we lose the symmetry of the space, and the geodesic are different because there is a direction that is favored. And so here the geodesics are represented in SE2 and are computed with a numerical integration scheme. And in a similar fashion, we sample another tangent vector and parallel transport it along the geodesics. And then we measure the error with respect to the number of steps of the integration scheme. And we compare this method to the pole ladder, which Elodie already described. So it consists in iterating this constructions of parallelograms, and it converges with quadratic speed. However, in this case, we don't have the geodesics in closed form. So the computations are slightly more complicated than in Kendall shape spaces, where the exponential was computed with cosines and sinus. In this case, we also use an integration scheme to compute the geodesics. And the pole ladder also works in this setting, where we replace the exponential map by one step of the numerical integration scheme, and the logarithm by an approximation of the inverse of this numerical scheme. So gradient descent over the initial condition of the exp that is only one step of the fourth order numerical integration scheme. And in this case, we've shown in previous work that pole ladder, the error is controlled, and pole ladder still converges with quadratic speed. Oh no. So it's the wrong way around. Sorry. This is a convergence plot of the three methods, where the first one is the pole ladder, and we retrieve the speed of order 2, and then we compare the room quota with a second order numerical scheme and a fourth order one. And as you can see, they converge much faster, and they're very stable when we increase the number of iterations of steps, whereas pole ladder is less stable. And we plot them for two different metrics with different values of the coefficients. But the implementation is not very sensitive to this change of metric. So to conclude, in this work, we've leveraged the invariance of the metric and of the connection to formulate the parallel transport equation in a convenient way in the Lie algebra. So all the computations can be done with matrix computations, and this results in a stable implementation of parallel transport that is available in our open source package geomstats. And the implementation is generic, so it's available on different Lie groups and different metrics that can be set by the users. So thank you for your attention, and here are some references, and if you have any questions, please ask them.
Thank you. Do you have questions?
Thank you for a great talk. I'm really excited to see this new method for computing these geodesics. I'm working on supplementing geodesics with a very similar method that you post on the example slide. And maybe you can show it again, because there's a question there. Maybe firstly, could you explain the presence of the omega squared in the method?
So maybe it's not the best notation, but I was referring to the usual metric on rotations. So actually in 2D, there's only one parameter, the angle, right? So it would be the omega squared.
So we can leave it out?
I'm sorry?
Could it be left out in this metric?
Yes, it could be left out, but it wouldn't be a positive definite metric on the whole group.
Okay, yeah, I see. So this is ensuring that. Yeah, so my question was really about the numerical stability. So do you see that this approach is more stable? For example, if you track of beta, you get a more and more anisotropic metric, and I can imagine that results get more unstable. Do you have an idea of how stable is this compared to other numerical schemes?
So I haven't really done the comparison with other schemes for the geodesics. So I don't know exactly. But yeah, and I haven't tried very extreme values for beta. But I guess symplectic integrators could be easily implemented and used instead of the room quota one. And yeah, it would be indeed interesting to compare them.
Okay, thank you.
Questions? Maybe I have one. You in the talk, the previous talk by Elodie, there was a balance between the accuracy of the method with the equations compared to the pole ladder, with the fact that the integration of the equation requires more computations. Is it the same here? Is there also, because you show a performance result, but I was not, is it the speed against?
No, so this is accuracy against the number of discretization step that we use. In terms of speed, pole ladder, the main problem of pole ladder is that we use a logarithm in the process at the midpoints, and this is usually slower than the forward exponential. And in the integration schemes, we only use forward applications. But in fact, so the best thing to do to improve pole ladder would be to be able to reformulate this as a symmetry and try to have a computation that is a symmetry directly instead of computing first the log and then the exponential. And maybe it would be more stable and a bit faster. But I don't really have ideas of how to do that.
Other questions? Any questions on the... Okay, thank you. So thanks again.